So with today's topic, I'd like to introduce Imad Al-Qadi. He is a Bliss Professor of Engineering at the University of Illinois at Urbana-Champaign. He's also the Director of the Advanced Transportation Research and Engineering Laboratory, ATRL, the Illinois Center for Transportation, ICT, and the Smart Transportation Infrastructure Initiative. Imad is doing lots of great work down at the University of Illinois, and he also worked at Virginia Tech before that on the Virginia Smart Road from 1990 to 2004. So with that, we also have Dr. Hasan Ozer, who has his PhD at the University of Illinois at Urbana-Champaign, and he works as a research assistant professor there since 2011. He's working in the areas of pavement material characterization, pavement rehabilitation and preservation, life cycle assessment, and use of computer-based. He's working on different mechanisms using computers for mechanics and structural performance and modeling of pavements. So with that, I'd like to introduce either Imad or Hasan. Go ahead and take it away on your presentation, and thank you.
Thanks, Ben. It's our pleasure to do this, and the way that we have this structured is I'll go through half of the presentation, and then Hasan will take over, and at the end he also will run the tool and show you a real example. So before we start here, I would like to acknowledge the support that we got on this work. We will be talking about two tools actually, but the example we'll be giving using one tool. The two tools that we developed is one for the Federal Highway Administration, and that was on the life cycle assessment for in-place recycling. And I would like to acknowledge some of our colleagues who work with us from UC Davis and from Rutgers, as well as several students here at UIUC. The second one is working with the Preservation Center at Michigan State University, and we developed a tool for the preservation. That's actually, it is in the last stages, so it's almost done. So that's why we thought we can present this to you just before, I guess, it's submitted to the center. So I would like also to acknowledge some of our partners from the Michigan State University, as well as from the University of Illinois here, our colleagues and students. So before we start here, just to make sure that we are all on the same page, you all are aware of the condition of our infrastructure, regardless if that's roads or bridges or dams or waterways, or even the rail system, the schools, the transit. So all of them together, we're giving a grade of D+. Actually, the roads are even a little worse here, which got a grade of D. What does that mean for us? This means here that there is a loss of each family income around $3,400 per year. The investment needed in order to get everything back to normal is around $2 trillion, with an annual investment that it's needed around $200 billion. If we do not do this, there will be some significant consequences. That's going to be including an impact of almost $4 trillion on the GDP. As you know, that the transportation system is contributing almost 10% to the GDP. There will be a loss in the business of around $7 trillion, and there will be a reduce in the employment of 2.5 million jobs. So we wanted to combine this now, this impact here, and see what's going to be the impact on sustainability or on the environment. Before we go through this, I thought that I will share this picture here from the National Geographic that's almost like 9 years old when they presented. The whole concept behind this picture is to tell you what is the real impact on the environment that we are seeing these days. There is a production of almost 9.1 billion tons of carbon and we are processing almost 5 of that, which means that there is an extra 4.1 that they're going to go to the air. Of course, there is almost 50% of that goes to the air already, but now we have another 5, which double the amount that it goes to the air. Now it's going to go to the air again, and that will definitely results in the global warming. Accordingly, when people met in Paris a couple of years ago and they came up with the Paris Accord, there was a reason why they wanted to control the increase of the temperature to 2 degrees just above what we had prior to the industrial era. So in this case here, there is some significant impact on the environment coming from what we are doing every day. Why we are talking about this? Because the transportation is responsible for 27% of all the emission or greenhouse gases that it goes to the air. And this is coming from the different modes of the transportation, and building pavements is still also part of it. Please notice here also that more than 90% of that emission, it comes from fuel that we're using in the transportation. So transportation system at 27, or this year even 28%, we have some significant responsibilities in order to reduce the emission and the greenhouse gases. Let's have a snapshot at the transportation related emission in the US here. So the greenhouse gases emissions per capita is around 20.2, and that's almost 4 times what is the average worldwide. Our share in that greenhouse gases as a country now is 15%, which put us number 2 in the world after China. And the transportation greenhouse gases emission per capita is 5.45, and as I mentioned, we are responsible for almost 27 to 20% of the total greenhouse gases emission. But also this is having an impact on the human health, and that's an average of 45 milligram per meter cube, and that's the air pollution, and that's almost 4.5 times what's the average that we have in the world. So let's go now into the pavement and see, as we are trying to build a pavement that is satisfying our customers or the riders or the drivers. We wanted this to be durable, we wanted this to be sustainable and safe, but at the same time, we need this to be economically valid. We need to reduce the greenhouse gases, and at the same time, we need to have the least impact on the societies that we have around us. And that's where the idea of, if we are looking into the pavement system, we need to look at it from the cradle to grave. We need to look at the holistic thing. And accordingly, although the investment, what appears usually for the decision makers is how much we are paying upfront, but there is future hidden costs that actually we can make them unhidden. That's involving the maintenance and the use of these facilities, the rehabilitation, the recycling, disposal. So all these things we can account for. Accordingly, we're going to be looking into the life cycle way of the pavement, and that's involving both the life cycle cost analysis, so from economic point of view, as well as the life cycle assessment, which going to look at it from the environmental point of view and see how we can have a whole cycle considering both economics as well as the sustainability. I'm not talking about economics today, but we'll be talking about the sustainability part. So whenever we talk about sustainability, I'm going to make this statement here maybe very clearly. If we do not save money, then I can tell you nobody going to be using it. So let's be clear about this. If we are trying to apply any sustainable solutions, we need to accompany this with an optimization that will allow us to save money. But at the same time, it should not be at the expense of the durability of the pavement. So we need to achieve the goals or the engineering goals of the pavement. We need to look at this as part of the holistic system and to preserve and restore the surrounding ecosystems and make sure that we are making an efficient and effective use of the resources. Accordingly, there is two ways to look at this in general. The first way is to look at it using a program like the INVEST that it was developed by the Federal Highway Administration, or the carbon footprint. What's unique about this program that it will give you the big picture about what's the impact on the environment. So it's a qualitative program. The one that we will be talking about today, it's more the life cycle assessment, which is a quantitative impact on the environment. So in the case of the life cycle assessment, we're looking here into the pavement from the cradle to grave. We have to look into all the stages, these stages including the materials, construction, maintenance, use, and end of life. And each one of them, they do have an input, which is the fuel, the electricity, the resources, and then you have the output, which is the emissions that it's going to go into the air or the water or the soil. And each one of them, it's involving so many different processes. Like, for example, the raw materials, it's involving so many activities that it has the input and the output that I talked about, the transportation, the mix production. Then you go to the construction. There's many equipment that they are involved in the construction, transferring the materials to the site, placing the material, then the traffic delay during the construction. Then during the life of the pavement, there is the maintenance and rehabilitation and repair, and all of that involving transportation, involving materials, and so on. The biggest contributor is usually the use phase, because that's where the vehicle is using the road, and there is many impacts coming from the pavement itself, such as the rolling resistance, the albedo, the lighting, and usually this constitutes big part of the life cycle assessment for the pavements. Then at the end, it's either we're going to put this in a landfill or recycling or both. So that's involving also the transportation as well as the use of equipment. So here's an example to put everything in perspective. Let's assume here that we have an asphalt plant. As an input for the asphalt plant, you bring the aggregate. These aggregate, they're going to go through several processes, from crushing, first putting explosives to get the aggregate from the mountain, and then after that it goes through many different crushers, and during that period also there is a transportations within the quarry. The vehicle can be idle or it can be moving and so on. So there is many different ways that the fuel has been used during this process. Then you get into the binder, and there's a big difference if this binder is coming from Venezuela or coming from Nigeria or coming from Saudi Arabia. The transportation of the binder, the flaring of the binder. So we have a program actually, or a model for the life cycle assessment of a binder that of binders that we have developed a few years back, that if anybody's interested on that. So after that, we have to transport all these materials to the plant. During this time, of course, the plant has to use energy. This energy is coming from gas, from coal, from fuel, from electricity grid system. For example, in the state of Illinois, we're using nuclear, and in nuclear, they are cleaner. So we have 70% of the power is in nuclear. So that will definitely reduce the emission. Then you look into the output here, which is the greenhouse gases and emission. So let's look now into a mix. If you look at mix, we looked into 1,000 mixes, and we looked into they have different binders, and we looked into the energy that went into these mixes. And surprisingly, you can find, like, most of our mixes are within 5.5 to 6%, let's say, binder. So if you look at that number, you will find that the energy that it went to this 5.5 or 6% binder is almost 80% of all the energy that it went to the mixes. So the binder itself is the most contributor to the energy use, and accordingly the greenhouse gases and the emission. So we need to do something about this. That's why people think about biobinder or using sulfur or using rehab. So it's not just saving the money, but it's also saving the energy in the plant. Here's a good example where we're showing here if we are doing a hot mix asphalt with different mixes for a pavement. First, we are removing the shoulders, we are removing the pavement, we're putting some granule embankment, and then we're putting some different mixes. And these mixes include, excuse me, warm mix asphalt for the subbase, hot mix asphalt for the shoulder at 6 inches, warm mix asphalt at 9 inches shoulders, and we have full depth hot mix asphalt 12 inches and 15 inches. So let's look into the percentages that we have of the energy for each one of the steps. Like the first, the material production, you will find that there's nothing in the removal of the pavements, but there is significant regarding the granule materials as well as the mixes. And please notice that these numbers are in percentage. As we transport, we need to use more now for the pavement removal, the shoulders and the embankment, but it's going to be less for the hot mix asphalt itself. For the plant itself, there will be more energy for the asphalt, but there is nothing almost when it comes to the removal of the materials or the embankment. Then we go to the movement or transportation on site. You will find that this is more related to hot mix asphalt. And the use of the equipment, you will find that it's mostly happening during the removal of the materials and putting the granule materials, and much less for the hot mix asphalt. Now, if you look at the distribution here, you can see the different activities, how much percentage each one is having. But if we are looking at absolute numbers, you will see that the absolute numbers telling us that most of the energy is happening in the hot mix asphalt, although we were seeing different percentages for the removal or the granule embankment, but their energy use is very minimum compared to the hot mix asphalt. So this is an example to illustrate to you why we have to look into this activities, and we look at it actually from a pay item approach, which is used by the contractor. Therefore, if we are looking into the pavement itself, usually as the pavement becomes rougher, we'll try to do some small repairs or major rehabilitation in order to restore the profile of the pavement itself. What we are proposing is that we should be looking at this from a different point of view, from a multi-objective pavement management point of view, where we have to consider the cost, the energy, and the condition of the pavement, and try to minimize the cost, maximize the condition of the pavement, and minimize the energy as we are going through this process. So that definitely going to be impacting not just the cost, but it will be impacting the environment. That's an introduction to take us to what we wanted, why we are doing this, and why we are going now into the sustainable pavements. So here's the two examples. One of them is to use the microsurfacing and see how this is going to be benefiting the environment. And the recent case that was done for in-place and in Virginia, that was called in-place recycling, and they did this on I-81. And they did it again on I-64, or they are doing it on I-64, and that's on the interstate. So this is the first time that called in place is done on interstate, and they realized that they can have some significant saving on this. Actually, we have a tech brief that is going to come out through FHWA maybe in the next month or so about this particular project. So that creates some questions here, such as, what is the existing condition of the pavement? Are we getting the same performance? Why we are doing this? If we are doing in-place recycling, is that because there is no good aggregate around, or there is no hot in-place plant? If we are not doing this, what is the optimum treatment that we have to do? Are the contractors in that region familiar with these kind of activities or these kind of treatments? After we are done, is the pavement going to be recyclable or not? These are all questions that they should be asked when we are doing something like this. So with that in mind, we have a methodology that we put together to develop a tool. And this is including collecting information from and data from contractors as well as agencies, and that Hasan will talk about this here in a minute. And we looked into developing a methodology and framework for both in-place recycling, preservation, and we have to compare this to, of course, conventional hot mix asphalt placement. Then we have to develop some models to look into the life cycle expectancy, and that's based on developing models, as well as when data is not available, talk to the agencies and based on questionnaires we receive or response to questionnaires that we send them. Then we developed regional life cycle inventory for all resources, and we were following the ISO as well as the Federal Highway Administration Life Cycle Assessment Framework that Hasan and we were part of that. And then at the end, we developed a friendly tool that based on VBA or Visual Basic Applications. So here's just a snapshot of the tool that we submitted to the FHWA. We don't know when they're going to release it. This is for the in-place recycling. So if you look, for example, at the main input page, this is information about the road, how much information they have about the condition, what kind of data they have. All this information, if it's available or not, it will be as part of the input, and accordingly, we develop what's the best treatment based on the information that's available, because some states, they may have like the condition index available, the pavement condition index. Other states, they have almost nothing, maybe visual survey, or maybe they have the rut depth measurement. So it depends on what you have. We'll be able to tailor the solutions for you. Then we came up with 35 different treatments based on the questionnaires for the different states, and the life expectancy based on the data available in some regions, such as California, and in others, we left it up to you as the user to define. If you have your, like Minnesota, for example, they may have their own life expectancy for a specific treatment, so they will be able to enter theirs. So again here, to summarize what I just said, we have 35 different maintenance rehabilitations treatment that we used, and that's include both cold in place and recycle place for that tool. And for the other tool also, we have similar treatment. Most important thing here that will allow us to compare for the in-place recycling for the conventional mixes. So now I'm gonna move this to Hasan to talk about the data that we collected and how we put it in developing this tool.
All right, morning everyone, and I hope everybody can clearly hear me. And I'm going to take over from here. We have 20 more slides left. We need to cruise over some of the slides, so we have some room left for the demo. And the inventory data collection and analysis in any LCA is the most time-consuming task, and it takes pretty much 80% of the time when you really perform any LCA. It is very data intensive, and you may need to go multiple resources to be able to collect the required data. And as you intend for a higher quality data, then your work, of course, becomes even more intensified. Our approach in this study and also the preceding studies was to go for commercial inventory databases. We purchased the software to be able to really access this commercial, very good quality databases. But we also employ other resources such as surveys and questionnaires. We conducted multiple surveys throughout this FHWA study, and as well as the new study for the University Transportation Center. You may have received our surveys along the way. And we also go for open public resources, literature, government reports, for some background data. And then we, of course, perform some simulations using this commercial databases and this LCA software. And this LCA software is called CIMAPro. There are multiple other programs available in the market, but we typically use CIMAPro because of its user friendliness and also availability for the academic settings. And at the end, we get our inventory models. Inventory models are those really required to, let's say, calculate the impact of asphalt mixture production, binder, aggregates, and everything that's being used in the production of pavements. And we perform at the end benchmarking with some available data to make sure that our results are making sense. So in this FHWA study, and as well as the University Transportation Center study that resulted in these tools that we were talking about, we conducted surveys. And in the survey, we went to the contractors and we went to the agencies. We got really good response from the agencies. We were targeting the state DOTs and counties. We have found that 15 states have responded to our survey for the HIR, and then 10 of them had some experience with HIR. For code in place and FDR, we got 19 states responded to our survey, and then 17 response, and then 2 no experience. We compile all of this information for primarily coming up with some decision trees and life expectancies for those treatments. And we have closely worked with several contractors, and the way we work with the contractors, we communicated with them one-on-one, and there were several contractors, called in place an HIR contractor, who helped us really build our database. And we work with one contractor for HIR and 2 contractors for cold in place and full depth reclamation. And the kind of data we really targeted with the contractors is, some project information. We wanted to access their projects that they have conducted in the recent years, at least in the last 3 to 5 years. What type of project, where it is conducted, and the type and number of lanes and the traffic, materials information, fuel usage. We wanted to access their logs, how much fuel that they actually consume during the construction, and also the construction equipment and productivity. One example of this data that we received from one of the contractors after in a series of conversations is, this is, for example, more than 10 projects that was performed by these contractors, and this is a cold in place recycling, and then we can see a clear at least results of presentation of the results in terms of fuel usage per square yard of different kinds of equipment used in the cold in place recycling operation. In this particular case, the contractor used 2 types of trains, and then we can see the majority of the fuel usage is concentrated on the milling operation with the green bars of this fuel usage record. And of course, it changes from project to project. Our job in this work is what really made those changes. In some of the projects, we see a very high usage of fuel usage. In some projects, we have a very little usage per square yard. So that's our objective, is to find out if there are any trends that we can identify to be able to use in our program. And this is just another example that is a result of our work with an HIR, hot in place recycling contractor. We have 3 types of HIR processes that we at least try to collect the data. And the majority of the energy usage in this case, as expected, was going for the propane consumption, as the heaters, and then some of the trains were using multiple heaters, and they were really consuming almost everything in this hot in place recycling operation. And there is, of course, a lot more data needed. This is just the construction, and the data that we call background came from fuel and electricity production, material production and processing, hauling and transport, equipment usage. These are all of the processes that we needed to collect data. And some data came from the commercial databases, and some data came from our inventory databases that we have been building since 2013. And we were using multiple resources to build this database, including EPA's MOOS, that's for the simulation for the traffic and construction equipment. We have electricity databases for eGrid, and we have Argon's program grid for some of the fuels, and we were also using U.S. Energy Information Administration's open database for energy resources for especially refineries. And one thing that we really paid attention in the tool is the hauling and construction equipment and hauling. And because we know that when you compare in-place recycling techniques, the benefits can only be realized if you can accurately capture the hauling of the conventional methods, hauling consumption or hauling related impacts associated with the conventional production of and transportation of the asphalt mixture to the job sites, because that's the one that's being avoided in the in-place recycling operation. So that's why we thought that we needed a precise model for the hauling. So that's why we performed thousands of simulations using this program called EPA's Environmental Protection Agency's MOOS program. And in this program, we performed the simulations considering different vehicle weight, payload, road grades, temperature, relative humidity, to be able to represent different regions in the United States. And this is just an example out of this hauling model that we developed. And this says, for example, what it really shows in here, the hauling impact in terms of greenhouse gas emissions as it varies from distance of hauling, from 25 all the way to 100. And it's obvious impact when the distance increases, but we wanted to see how this really is changing with the payload. So there is some really changes with the payload, but the dominant factor is the payload, is the hauling distance. So it will be very important for us, especially when you compare in-place to conventional, to accurately capture this hauling distance related impacts. And in this particular case, another example of how the hauling impact changes with grade and also the distance of hauling. Again, the same information, the bars are showing the hauling impact as the distance increases. We see the similar kind of increase in the greenhouse gas emissions with the distance, but we also see with this box plot the range of really impact associated with the grade. So grade is also an important factor, almost as high as the distance. So it really depends on where you do the hauling. In a flat region like Illinois versus in a different region where you have higher grades, will definitely impact the distance-related greenhouse gas emissions. So these are the kind of really factors. In addition to those, there were many other factors we wanted to capture to make a precise prediction of the hauling impact on the energy consumption and greenhouse gas emissions. And one other impact, I think, aspect of our tools that we developed for this in-place recycling is the life expectancy. We know that it will really be important when you compare any type of preservation or rehabilitation treatment. We need to know how long they will live. So that's why we developed different types of life expectancy models. And they were needed especially for compiling a maintenance and rehabilitation schedule, but also develop a use stage IRI progression models. We followed different approaches. And one approach is what we call the multi-criteria performance estimation. We basically calculated the risks of the treatment based on certain conditions like existing pavement traffic, the treatment itself, the material type used in the treatment. So we gave some kind of a score for every treatment, and then we estimated the lifetime for that treatment for the in-situ conditions. And another type is the deterministic. Given a pavement performance condition data historical, we built some models for some of the treatments, especially if the data is available. We incorporated that also in our tools when there is historical pavement condition data is available. And the way it's implemented in the Federal Highway tool is we have the life expectancy graphical user interface, and you can see in here, let's say we're dealing with microsurfacing single scores, and the score for this particular case is 2. That's a low risk situation. Our score was going from 1 to 5, and we have now an estimation for this really treatment that really enables us to draw this IRI progression curve, and it also shows us how long the treatment will live in the job site. But we also allow the user to change this, because this is our initial estimation, and then the user may say, hey, in my region microsurfacing lives much longer than that, and they can just basically, using this slider bar, they can change the number of years this treatment will live depending on their regional experiences. And the other snapshot is from the deterministic model, which comes from basically a model that employs some coefficients if there are historical pavement condition data and those coefficients are available. I'm going to now present several use cases in the last 5 minutes before we move on to the demo. And these are some of the use cases of the IPR tool, which is the Federal Highway tool submitted to administration a while back. In this use cases for this IPR tool, we selected a design. We selected 2 comparative designs for an existing structure of 4-inch HMA surface course, 8-inch crushed aggregate base on a CBR of 6. We came up with 2 different types of treatments and used IDOT's Bureau of Local Materials, and in this case, the cold-in-place recycling design included 3-inch cold-in-place recycling, half-an-inch chip seal over the same base layers, and for the mill and fill conventional treatment, we have 2-inch HMA overlay over this 8-inch crushed aggregate base. So we were comparing these 2 cases using our APR tool, given the conditions in this slide with the traffic volume of 800 AATT and the truck volume 5%. And we are assuming that these 2 treatments will live 20 years. And this is just an initial results, a quick look at the results, how the conventional treatment is compared to cold-in-place recycling. And this is the energy consumption per lane mile for each treatment. And this is the cold-in-place recycling, and the blue bars is the impact related to materials, the red is the construction, and the yellow is the hauling. And this is the case where we have 0 distance of hauling. So in here, still even the distance is 0, we have quite a bit of saving with the cold-in-place recycling. Of course, the condition is that they are going to live an equivalent amount of, provide equivalent amount of service life. And in this case, a scenario, for example, when you increase the hauling distance, now the yellow bar you can see in here is increased dramatically because of the hauling impact that comes from the transportation of the asphalt mixes from the from the plant to the job site. And then in that case, the more savings can be realized when the hauling distances increases. This is just an example of how the tool can be used to demonstrate the savings. And we looked at, of course, multiple different things, parameters, what really changes those savings. And this plot, what we are saving is what we are showing in the energy savings. So the savings can be from 20 to 45%, and we are comparing these two cases, the conventional versus a cold-in-place plus a chip seal case. The orange bar is a 0% grade, and the blue bar is representing an 8% grade. And you can see when the grade increases, of the grade of hauling increases, we can even realize much higher savings. And this is the kind of things that can be used or quantified in the tool to demonstrate the savings of in-place treatments of any other preservation treatment as compared to conventional treatment. Of course, again, the big assumption in here is that we are assuming that these two treatments are going to have the same equivalent amount of service life, provide the same and similar performance. And then now Virginia case, I think Dr. Al-Qadi mentioned this at the very beginning of his presentation, and this was a study that we at least collected some data from Virginia DOT, and it will be a part of this Federal Highway Tech Brief. And it was a construction on I-64 and I-81, and it was including the cold-in-place recycling, cold central plant recycling, FDR. So it was the first, I think, one of the first, at least, examples of all three of the in-place recycling methods being utilized in a construction project. And they were really having significant cost savings. It was reported as, especially in the I-64 construction, they reported $50 million out of $300 million plus construction costs. And what we did is, using our tool IPR, we wanted to demonstrate the environmental savings. And we did this for I-81 and similarly for I-64, but I'm showing you in here the results from the I-81. These are the structures used in the construction. They have 4-inch new HMA in the left lane, 5-inch CIR, and existing AC, a much thinner structure, much less traffic capacity, structural capacity. On the right lane, we have a much stronger structure. We have 4-inch and 8-inch, 6-inch and 8-inch CCPR, so much higher, at least, bound layers on the top, and on top of 12-inch FDR. And what we're showing in here is the conventional treatment, which wasn't built, obviously, but if they wouldn't use the in-place recycling treatment, that's what they would have built. And as compared to that, the left and right lane treatments used in the study, you can see a dramatic drop in the energy demand. And we have similar numbers for the greenhouse gas emissions and other environmental impacts. That really shows us that in addition to cost savings, in this particular project, there were also significant reductions in the environmental impacts. And this I-81 was built in 2011, and the performance of those sections are satisfactory according to Virginia Department of Transportation's historical performance data, condition data. So with that, I'm going to just wrap up the presentation part of this webinar with some summary remarks, and I will move on to the demo. And we believe that we need high quality and relevant regional data, and especially if we want to compare in-place recycling treatments against the conventional treatments. So that's why we built this user-friendly LCA tool that allowed us comparing various preservation and rehabilitation alternatives. And we believe that we accurately captured the impact of construction and hauling activities in addition to other life cycle activities. So with that, I will switch to the demo. And I hope that everything will go smoothly. Bob, are we still good?
Yep.
Good, excellent. So I will use it maybe 5 minutes to demonstrate the use of this at least one of the tools developed with the preservation and rehabilitation being the focus of the tool. And this is the tool that we improved over the Federal Highway Administration tool that was submitted to them. And this tool was developed for University Transportation Center. And it's more comprehensive than the tool submitted to Federal Highway because we included some of the concrete surface payments as well. But the data and the working principles are the same. So we have multiple options in here for the initial stage. We wanted to develop the tool using the pay items because we believe that's really important for consistency with the procurement processes. So it makes it also much more convenient for the agencies to be able to adapt the tools if we really use the same language that they have been using with the contractors. So that's why we have the option in here to import your pay items to this tool to be able to really run the LCA for your treatments. I'm going to perform an analysis in here. I'll show you how we can really at least carry out a simple analysis if we use this Excel-based tool. We have this initial page. What I need to do instead of creating a new project for the time being, I will load an existing project that we have worked before. And we have some project information, and we can choose Minnesota for this project location, the time, number of lanes, some notes that you may want to take, and the total mileage of the project. So this takes us to the main at this page of the program that we can go between the life cycle stages. So we have different life cycle stages in here: preservation, maintenance schedule, materials and construction and use stages. And I'm going to show you what the main inputs, how the main inputs look like. We have typical information. Some of them are recovered from this initial project information page. And we have the traffic information in here, structural inputs. And the next thing, once we are confident about the main inputs, we go and then schedule a treatment cycle for this particular case. And this was a case, by the way, an asphalt overlay on CRCP, the particular example. So we're going to have a schedule set up in here, and this is the important part of the tool. We spend a lot of time in really building this part of the tool because we want the users, the agencies, to be able to build any type of really scheduled cycle for them. That includes heavy preservation, light preservation, or only conventional. So many options is available to the agencies to be able to really tailor this part for them, for their practices. And in order to be able to do this, for example, this is set that we have initially thought that, okay, maybe we need initially a microsurfacing. A lifetime estimated for this microsurfacing is 4. Maybe we may want to think about a thin AC overlay after that, and we can really final the treatment that we can choose for this case can be a CIR and microsurfacing. In order to be able to make the selection, what we have is this distress inputs, and in the distress inputs we ask some questions to the user, such as, for example, do you have some structural problems in this section? If there are structural problems, we ask the distress severity of fatigue cracking and extent and rutting as well. Let's say in this particular case we have medium fatigue and low rutting, and this tool really gives us some of the options, and you can see many of the options that are eliminated because I've selected that the section has a structural problem. So this only gives us the option that is really something we consider as heavy rehabilitation, because the section is experiencing some structural issues. But if you don't have structural issues, you may really see that there are many of these options available to you to choose at any as part of your scheduling activities. And another important feature of this this graphical user interface is the ability to apply or add pay items. So in here, let's say thin AC overlay, we have the milling activity, and we have the thin AC overlay, and those are the pay items uploaded already to the system. But you have the ability to add or remove the pay items according to your practices. So this is how the at least the scheduling phase looks like. And if you move on to the material and construction stage, we have the list of pay items. So these are the pay items at year 0 that are related to microsurfacing, year number 4 that are related to thin AC overlay, and year number 9 is the cold in place recycling and the microsurfacing. I'll pick one of the pay items in here if I can find. Okay, this is the thin AC overlay. And this pay item, you can see it's pretty detailed. And then we have the pay item, some information about the pay item, what is the name, date created, unit of the pay item, square yard, productivity, cost, and some other information. But there is also other supplementary information that is needed for this pay item for characterization of the pay item, such as the mixture. So we know for this thin AC overlay, let's say we are using an HMA mixture identified as this design ID. That's a design ID used by IDOT commonly. That's for this particular example, we chose that. And you can go in and edit your mix design. if you want to maybe put another mix design for this treatment, then you can just change that mix design and then save it and then make it as part of your treatment. And the next stage is the use stage. After we are done with the treatment scheduling and the materials and construction and the pay items, we initiate the use stage. And the use stage consists of three parts. And one is heat island, IRI progression, and texture. Heat island is something that really was done by our group in here, Professor Rissler and his students. And in this case, we are looking at the energy balance depending on the surface cover. You may have heard about this albedo changes with concrete and asphalt pavement. So we are basically quantifying the impact of that in this tool. And the next one is the IRI progression. And we have the IRI progression of the selected treatment in here. And we have also a case, a hypothetical do-nothing case, in case you want to compare how much you're saving if you don't do anything in this section. And this is based on the roughness impact. And the last one is the texture. We account for the impact of the texture on the fuel consumption as well. So we have the texture numbers associated with each treatment in here. We assume for this tool, the texture remains constant because of the duration of the treatments, because they're small and relatively short. We assume that the texture doesn't change during the duration of this preservation treatments. So this is the impacts associated with the use phase. And the final stage is the review of the results. So in this case, if you go and then calculate everything, we have a simple table that really shows the results of the entire project, material and construction. We didn't choose to work with at the work zone in here. And we see a present cost. Cost numbers are not accurate at this point, but the environmental numbers are calculated according to our inventory databases and analysis. We have the global warming potential and energy, and we can also graphical results represented by this pie chart. So in this case, depending on the traffic condition or the material usage, use phase really constitutes a significant portion of the impact, up to 68%, and then we have a significant also impact coming from the material and construction, about 40%. So that's how the latest version of the preservation life cycle assessment tool looks like. And with that, I think this concludes our presentation and the demo part. And I'll be glad if you have any questions, we'll be glad to answer. Bob, I'm turning it over to you.
All right, Ben, are there any questions in the room?
I guess there are any questions in the room for Art?
Come on, Ben, I got a question.
Go ahead.
Can you hear me, Ben? This is Glenn.
Yep. Go ahead.
So great presentation, very impressive. I work for MnDOT, and we're developing a pavement investment guide that looks at optimizing our investment over the entire system, and we're looking at measures of basic percent poor and good, and then remaining service interval, asset sustainability ratio, cost per lane mile per ESOL, vehicle miles traveled on poor roads and good roads. So we're having a lot of measures, and we're also potentially, I can see how this would fit into that. So any comments on how you can look at this type of work related to optimizing it over not just a project, but over the entire system?
I'll take the first shot. Actually, the whole idea is to have this applied for the network. I mean, that's going to require some significant work, but that's ultimately where this is going. So this will not be just a project by project, but our goal is to have this applied for a network. That's the ultimate goal, of course. But at this time, it is applied for a project to show the importance of the sustainability and using this life cycle assessment. I mean, we'll be more than happy to discuss this with you further, for sure.
Yeah, I think that would be great because we're gonna. Our goal is to complete our pavement investment guide by next spring and get it out to the hands of our districts to start using it to optimize the investment on the system. So thank you very much.
Yeah, absolutely.
Just a quick question. Does your tool accommodate sustainable practices in concrete or concrete rehab or preservation, particularly in areas like pozzolanic substitution or the use of recycled aggregate? Because your presentation seems to have dwelt much lopsided towards the flexible side.
He's asking if the tool will accommodate the.
The example that I demonstrated was the asphalt flexible, but the tool included the concrete preservation techniques, and of course the preservation are heavy on the flexible side, but we were able to find some of the preservation techniques like grinding and some other concrete preservation technique, patching. Also included in the concrete side. But however, if you're interested in, let's say, if I change the cement type, what happens, for example, the sustainability impacts, or if I use recycled aggregate in my concrete mixes, and these are very easily integrated to the mix design because these are material-related, let's say, impacts associated with the mix design, and then we can tailor always the mix designs to incorporate different types of materials.
All right, we have one more question here.
Yeah, I have a question about the difference in energy that you saw, for an example, with CIR versus mill and fill. And I'm wondering about the significance of the difference in energy compared to, say, if the mill and fill were to last 5 years longer.
Oh boy, I mean, if I understand the question, did we look into historic data? Is that your question?
More simple, just certainly if a pavement lasts longer, you're going to use less energy. And I'm wondering the difference you were seeing in energy for the same amount of time, how that compares in significance to if the pavement lasts longer.
Yeah, I mean, I wish I added. We removed a lot of slides to be able to fit everything into this 40 minutes. There was a study that we did exactly this, and maybe the
slide is there.
I'll have to check whether it's in. It's probably not. So in this study, what we looked at is the sensitivity to see how many years that we can tolerate of losing with cold in place, for example, or some of the in place recycling treatments. I mean, in order to be able to really see still net gains. So according to that study, I think as far as I remember, you are still okay if your treatment lives, let's say, 2 years shorter than the conventional treatment. But after that, then you start really losing with that kind of a really in-place recycling. But you are okay up to 2 to 3 years. Of course, depends on the traffic conditions, some of the in-situ project site conditions. But we had this study. I can share that with you if you're interested in, because it was also published in a paper.
Yeah, and actually we have that. We did that for several studies we had before. Even when we did this for the RAB material that was published, we always try to do a sensitivity analysis that what if, let's assume that you are including RAB in your design, just for the sake of explanation here. If you are including RAB and your pavement design life is decreased by 1 or 2 years, are you still okay? So these sensitivity analyses are very important. So we do that, yes. Actually, this is off the topic a little bit. If you look into this, I mean, that's part of the Pro LCA that we are looking into the alternatives, to look into the alternatives and how much will impact the cost. That's a little different tool we have for that. We can share that with Ben, I guess, to let you look at it too. That's a different one for looking into the probabilistic and look into sensitivity analysis. Yeah, but your question is well taken. Actually, on a different tool that we developed, we did help the tollway to look at their development over the past 10 years to see how much benefits they have gained from sustainability actions that they have took. So yes, so as Hasan told you, the answer to your question is yes. Whenever we do these things, we do some sensitivity analysis.
Are there any questions online? We have one more question here in the room, but is there anyone online that has a question? Well, here's our question we have in the room.
This is Iyad from Imad. Can you hear me?
Yeah, but if you can speak louder, that would be good.
Okay.
Good.
First of all, very impressive presentation. You took VBA user from to another level. Congratulations on that. My question is, your presentation somehow confirms the expectation that coal recycling will save more energy compared to HMA. I want to ask if you want to compare two different coal recycling. For example, if your in situ pavement condition is different. For example, if you have more moisture pavement, or if you are including APR with different percentage of aggregate and RAB, like 20% or 80%, how would you be able to use your program to compare different types of APRs or CIRs?
I'll take the first shot at this here. I think in order to do that, you need to have a knowledge about the life expectancy if you are doing a change in the mix. So everything going to be depending on what is the life expectancy that you have to change. So if you are including 20, what's going to happen to your life? And that's why we are running the probabilistic approach and sensitivity analysis to tell you what kind of risk you may be taking if you are adding 20% and your life going to be decreased by 1 year or increased by a year or so. Hasan?
I mean, if also the question, let's say, if I need to change my mix design or the treatment, let's say, or the stabilizing agent, or the amount of stabilizing agent, and then those are the kind of things we can incorporate in the pay item. I've shown the pay item, and then there is materials and mixtures part of each pay item. We had some information needed for, let's say, for FTR and CIR that is related to the mix design of this this in-place recycling method. In there you can make those changes, and that will of course obviously affect the impact. And if you increase the cement, you may see the different stabilizing agents. You will certainly see an increase or decrease in your impacts, but it also will boil down on how long it will live if those conditions really that you are using in the job site to construct your pavements. But in the material sides, we can incorporate those.
Do you think in the short term, would these factors affect the construction, the compactive efforts when you have more moist material or more? Do you see that in the difference of construction operations? How would they affect the saving of energy?
Okay. All right.
Well, that's a good question. I mean, there's a lot of questions here, and I think that Imad and Hasan would be open for any questions you might have. This presentation will be posted on our NWRA website with contact information for both of the presenters. So give them a warm welcome, or a warm thanks. Thank you.